Step 3 of our hypothesis test is our test statistic. This is where we gather all of our evidence. In order to calculate our evidence, though, we need a couple things. First of all, we need to know how much variation do we expect. That is, sure, this sample gives us this value, but what about other samples? How spread out are our samples actually going to be? In order to find that, we need to go ahead and calculate an estimate for our standard deviation. And as we learned in confidence intervals, our estimate of standard deviation is SC, or standard error. Now, I want to remind you that in confidence intervals, the formula for SE was p hat, 1 minus p hat, all over n. It turns out our SE here is very, very similar. The only thing is, we're assuming that this p hat is not as good as our assumed value. That is, we're assuming that p naught is true, not p hat. That is, we're assuming, once again, p naught is a better estimate of what's happening in the population than our sample is. For that reason, our formula for SE has the same form. The only difference is I replace p hat with p naught. And this is for hypothesis testing, while the one over here on this side is what we use for confidence intervals. Now that we've got that, let's go ahead and talk about what we're going to do with SE. Once we find SE, that is how much variation there is between samples, the next thing we're going to calculate is our test statistic. That is a weight of how much evidence we actually have. The way we weigh that evidence is we go ahead and we calculate our z-score. Remember, z calculates how many standard deviations away from expected we are. We always calculate z by taking our observed minus our expected and dividing by some estimate of our standard deviation. And sometimes we have the actual standard deviation, so we plug that in instead. In this case, my observed is the proportion that actually happened in my sample, which is p hat. My expected value is p naught, that's what I'm assuming is true, and my estimated standard deviation is SE. So this will be the formula we use when we go about calculating our test statistic. Let's go ahead and look at an example now. Go ahead and pause the video for a second and read through the example again. This is the example we worked on when we were exploring step 1 in a previous video. I have step 1 down here with p hat, n, and p naught, but we need to go ahead and fill in step 2, that is, write our hypothesis for it. So moving this up just a little bit here, so we have plenty of room. Step 2, our hypothesis, always has two forms. It was h naught, our assumed value, and HA, what we're trying to prove. H naught is always P equals. In this case, we're assuming that, in fact, the film had exactly the same rate of cancer as the public. That's what we'd be expecting to happen. So P equals 0.136. HA is what we're trying to actually prove. So I'll have P in 0.136 there. Notice again that this value right here and this value right there are actually coming from P naught. To figure out what I want to put in between those two, I look at what I'm actually trying to prove. I want to say, can we conclude that the crew suffered a significantly higher rate of cancer? Well, if they have a significantly higher rate of cancer, P would be greater than 0.136. That is, the film crew should have a rate that's significantly greater than that of the public, 0.136 or 13.6%. Having done step 2, let's go ahead and do step 3. Step 3 is once again my test statistic. When I go to calculate, the first thing I'm going to do is calculate SC, which is square root P naught, 1 minus P naught, all over N. In this case, that'll be 0.136, 1 minus 0.136, all over 220. Now once again, if you're sketchy with your calculator, go ahead and simplify this first. That is, we can rewrite it as square root 0.136 times 0.864 divided by 220. Which will give us, after we go ahead and round it to once again 4 decimal places, 0.0231. This is our expected variation between samples, if in fact our assumption is true. Now we need to go ahead and weigh the evidence we have, which is we have to calculate our z-score. Moving up again, z is going to be equal to our actual value p hat minus our assumed value p naught, all over the estimate of our standard deviation, SC. So plugging these all in here, notice from above, we had p hat as a fraction. If I go ahead and take 46 divided by 220, I'll find out that p hat is right around 0.2091, minus p naught, which is 0.136, divided by our SE, which is 0.02231. Now, if you're going to plug this into your calculator all at once, make sure you put parentheses around the top of it. My recommendation is to simplify it first. So if I simplify this, I'm going to get 0.0731 on the top, divided by 0.0231, which will give me 3.16. A couple things about the z-score. One, it's positive. And it's positive because what actually happened, my 46 out of 220 people, is higher than the 13.6 I'd expect the percentage to be. That is, I'm getting a positive z-score because my actual value here is above my expected value. The other thing to notice here is that a z-score of 3.16 means we're 3.16 standard deviations above our expected value. If you remember the whole 1, 2, 3 standard deviation thing from before, being 3 standard deviations above our expected value is really far off. So that is, we have a lot of evidence here to say that maybe our assumption is actually not correct. Once again, this is our example of the third step of hypothesis test, our test statistic, which for a single proportion hypothesis test means we'll calculate SE and we'll calculate Z.